Hey folks, here we're going to be looking at the base ionization constant. So we have the acid ionization constant, which when we have an acid, it reacts with water to produce our conjugate base, which is A minus, and our hydronium ion. All right. So we're going to talk a little bit about when we have a base ionized. So that would be A minus reacting with H2O. In case you're wondering, A minus, what that is, or even just A is just a generic variable for acid. So A minus reacts with H2O to produce our conjugate acid, which is HA, and our conjugate base, which is OH minus in this case. So bases vary in strength, much as acids do. The only strong base is the hydroxide ion. So we have those six strong acids. We only have one strong base, which is the hydroxide ion. It is commonly found as part of an ionic compound. So a lot of times we'll see it with sodium or barium. And if I want to know the hydroxide concentration in a solution of an ionic compound containing OH minus, we have to take whatever it's a part of and dissociate it. So to find the hydroxide ion concentration of a 0.064 molar per liter solution of barium hydroxide, we begin with barium hydroxide, BaOH2 aqueous, is going to dissociate into Ba2 plus, which is aqueous, plus OH minus, which is also aqueous. To balance this out, I have two hydroxides here. I need two hydroxides here. Bariums are balanced. We're good to go. My concentration is 0.064 moles per liter. And then I could just move that using stoichiometry, multiplied by 2 over 1. And my concentration will be 0.128 moles per liter. All right. So that is just the basics of finding our concentration of hydroxide. Now we're going to look at some weak bases. So we've talked about the hydroxide, but now we're going to talk about weak bases. So in order to predict the hydroxide ion concentration of a weak base, we need to use the base ionization constant. So we had Ka, which is the acid ionization constant. Now we're going to be looking at more pen issues. The Kb, which is the base ionization constant. So the base ionization constant, nope, don't want that. The base ionization constant, Kb, is the equilibrium constant for the reaction of a base with water. So as I've drawn before, A minus reacts with H2O to produce HA and OH minus. My Kb, we know this as our products over our reactants, which would be equal to HA. This would be aqueous, but just to save a little time here, we'll just go over it with the chemical formulas, over A minus. So that is our Kb, is how we would find that. The concentration of the HA, our conjugate acid, conjugate base, over my initial weak base. And we know that Kw is equal to Ka times Kb. So we know that Kw, just quick review, is 1 times 10 to the negative 14. So we can just even say it's just 10 to the negative 14. And then Kb, to find that, we would just go Kw over Ka. So we can find Kb for any base we have on our table. The example it has for us here is determine the Kb for the carbonate ion. All right. So what I do is I'd start with carbonate, which is CO3 2 minus, aqueous, reacts with H2O, which is a liquid, to produce HCO3 minus, aqueous, and OH minus. Also aqueous, negative 2 on the left side here, negative 1, negative 2 on the right side there. We're good with that. We're happy with that. All right. My Kb in this case is going to be HCO3 over OH minus times these two together over CO3 2 minus. H2O is a liquid, so it's not included in there. But I don't need to find that way. I just need to determine the value of the Kb. So we had up here Kb is Kw over Ka, so Kb is Kw over Ka, and we know Kw is 10 to the negative 14 over my Ka, which I have to get from my data book. Now, when I look inside my data book, what I see is that it's going to be towards the bottom. I have HCO3 minus on the left side. I have CO3 2 minus on the right side. When we go from an acid, when we look at the acid ionization constant, we go from the acid formula to the conjugate base formula. Now we're going the opposite way, in which we have our CO3 2 minus becoming HCO3 minus. And my Ka is 4.7 times 10 to the negative 11. If you're not sure where that value came from, let me know. I'll make sure to find that for you. So 4.7 times 10 to the negative 11. When I get the value for that, it will be 2.13 times 10 to the negative 4. That's all I have to do on that one. Okay. All right, we're going to look at calculating Kb from amount concentration. So calculating Kb for a weak base uses essentially the same method as calculating Ka for a weak acid. In this case, a student measures the pH of a 0.250 mole per liter solution of aqueous ammonia and finds it to be 11.32. Calculate the Kb for ammonia from this evidence. All right, we have NH3, which is aqueous, reacting it with H2O liquid to produce, this is an equilibrium, to produce NH4 plus and OH minus, which is aqueous. All right. Now I have my ice table set up here, and it told me I started with 0.250 mole per liter NH3. The water won't have an effect. NH4 will be 0, OH minus will be 0. All right. And they give me this value here of 11.32. So this value of 11.32, it is the pH. So what I can do is I'm going to go POH equals 14 minus 11.32. And then my POH will equal 2.68. 2.68. That still doesn't give me what I need. What I need to do is I need to find my hydroxide ion concentration over here. So to find that, I'm going to go hydroxide ion concentration, OH minus aqueous, is equal to 10 to the negative POH, which we know, so OH minus is equal to 10 to the negative 2.68, and OH minus equals 2.09 times 10 to the negative 3 moles per liter. And that's my concentration of OH minus, which will go right here. So 0.00, oops, too many zeros, 0.002089. That's going to pop up again here for NH4, so 0.002089. This will be plus 0.002089 and plus 0.002089. This will be subtract 2.09 times 10 to the negative 3, and that's going to give me 0.2479. All right. That's just giving me my concentrations at equilibrium for this reaction. When I have found my, when I know my everything I have, my pH at equilibrium, and then my initial concentration. Now I have Kb equals my products over my, more pen issues, reactants, and then Kb equals NH4 plus H4 plus times OH minus over NH3. Pen is glitching in and out, kind of painful. That's my KB expression. KB, I'm going to take these two values here, and I'm going to go 2.089 times 10 to the negative 3. I'm just going to square it. It'd be times itself because NH4 and OH minus are the same, over my concentration of NH3, which is 0.2479. And my KB equals 1.76 times 10 to the negative 5. There we go. Oops. All right. That's my KB. I'm going to do one example here from the last page of our base ionization constant. I'm going to do number 1 here. Number 2 is just the second example, kind of showing how it's done. It's going to be the same. It's the same thing as the first example, just with they're using codeine. I put a negative charge on it just so that way the charges were balanced out throughout the reaction in that second one. But at the first one here, we're going to have sodium. We have to find a hydroxide ion amount concentration, POH and pH of a 1.20 mole per liter solution of sodium hydrogen carbonate. So they told me already. I'm just going to do it up here, just so it's out of the way. Sodium hydrogen carbonate. And this will dissociate into Na plus and HCO3 minus. Charges are balanced out. I'm not going to use sodium in my calculations. It would essentially just be a spectator ion. One of the things we know is that it doesn't have any effect, doesn't react as an acid or a base. So when we react it in our base reaction, it's just going to stay as Na plus. Whereas the HCO3 minus, we're going to take a look at right now, which is HCO3 minus aqueous plus water will produce OH minus aqueous plus H2CO3, which is aqueous. We know my water doesn't have an effect, as I set up my ice table, like so. And then my initial concentration was 1.20. My initial concentration for these two was 0 and 0. And then I'm kind of left on my own. I have to kind of figure out what I'm doing. So my Ka of H2CO3 to HCO3 minus is, let me just find it here. It's 4.5 times 10 to the negative 7. 4.5 times 10 to the negative 7. To find my Kb, I'm going to go 10 to the negative 14 over 4.5 times 10 to the negative 7. And Kb is 2.22 times 10 to the negative 8, like so. And now, once I'm there, what else can I do? Well, we don't know our N concentration. Like, it didn't give us a pH, it didn't give us a POH in which I can find out my concentration of OH minus here. It also didn't give me a concentration of H2CO3 at equilibrium or HCO3 minus at equilibrium. So what we do is we write this as minus x plus x plus x. We know at equilibrium it's going to shift to the right because we have nothing over here. So this is 1.20 minus x. This is x, and this is x. Now, I made a note on the side here in the notes that HA/A minus, as long as the concentration of that is 1,000 times greater than my Ka/Kb, there's my slash, as long as it's 1,000 times greater, then I can actually do this kind of a shorthand route. Because when I set this up, I know my KB is equal to my products, which is X times X, over my reactants, which is 1.20 minus X. This is equal to X squared over 1.20 minus X. When I move this over, what actually happens is that I'm going to move this over here, and then when I do, I actually end up with a quadratic equation. And we have the math to do that, and a lot of the times we don't need to use it, about 98% of the time. The 2% of the time we do is when that our concentration of our acid or our base is less than 1,000 times greater than our Ka or Kb. So I just simplify this here, cross the X out. I multiply 1.20 by my Kb, and what happens is that I get X squared equals 1.20 times my Kb of 2.22 times 10 to the negative 8. And then what I'll do is I'll just square root both sides to get X. And we find that X is 1.63. 1.6, it should be 1.63 times 10 to the negative 4. Not positive 4, has to be negative 4. 1.6 times 10 to the negative 4. That is my X value. And what is my X value again? My X value is my hydroxide ion concentration. So let's go back to the question. This is one of the big things, especially in any science that you have. Make sure that you actually answer the question. So I have the hydroxide ion amount concentration. Yeah, it wants me to find POH. So to find POH, I go negative log OH minus, and POH equals 3.787. I just plugged in this value here, over here, to get this. And pH equals 14 minus 3.787. pH equals 10.213. All right. I feel like one of the questions that would come up is, why did we have to do this thing where we made this assumption of X? And how come we couldn't do that up here? Well, in this one up here, this is essentially taking experimental data and finding our value of Kb. We said, okay, well, we have this much, a concentration here of this much, and we have a concentration here this much. What is our Kb value, our experimental one? Well, it's this. In the next example here, when we're calculating our OH minus, we're able to use our data book to use that Kb value. But once we do that, though, we run into the issues again of that when we set this up. It's going to set us up as a quadratic equation, which we don't like working with, but we can. And usually, though, we'll make that simplification and just cross this X off to leave our X squared. Make sure to square root that so you get the correct answer. All right. Hopefully that helps explain some of that. We have one more part for this unit, and then we are done it.